I'm recording. So exergonic reactions release energy, endergonic reactions absorb energy. So we're looking at what's happening with the energy during a chemical reaction. And so the essential questions that we want to be able to answer, we want to be able to identify the source of the energy changes in a chemical reaction. We want to be able to compare exergonic and endergonic reactions. We want to be able to compare exothermic and endothermic reactions, very similar to endergonic and exergonic. And then we want to see how the energy is conserved through a chemical reaction. So some new vocab terms for us are going to be the exergonic, endergonic pairing, and then the exothermic, endothermic pairing. And so what happens with the energy in a chemical reaction is based on how the bonding is changing. And so the chemical bonds are the source of the energy. And so whenever we are breaking chemical bonds, we require energy. So if I'm going to break a bond, I need to put energy in to break it. When I'm forming bonds, I'm releasing energy. It's a lot like magnets. Okay? If you have two strong magnets and you bring them close together, they're kind of pulling on each other, and as soon as they snap together, that pull is kind of diminished and all of that energy just gets released. It's like a relaxed state for those magnets to be stuck together. Okay, but when they're close together, they're pulling on each other. So when they finally link together like that, that energy that they previously had is then just suddenly released. It's the same thing with chemical bonds. Chemical bonds, when the chemical bond actually forms, that energy just gets released because it's no longer trying to use the Coulomb forces to pull them together. They're already been pulled together and they're already bonded at that point. And so when bonds form, energy is released. When you're going to break a bond, so think about the magnets again. If you have two magnets stuck together, you have to apply some force to pull them apart. Well, it's the same thing with chemical bonds. If you're going to try to pull those magnets apart, you have to have some type of energy input to do that. And so pulling them apart requires energy, just like breaking bonds. Pulling those atoms apart requires energy. So breaking requires energy, forming releases energy. Okay? And whenever you think about requiring or releasing energy, always think about a system. Okay? And so I'm just identifying my system as this little box here. If something requires energy, the energy has to go into the system. And so here's my energy going into the system. And so this would be bond breaking. And then if something is where the energy is being released, well, energy is then leaving the system. And so this would be bond making. So energy is either going in or it's going out. If energy is going in, then we are going to be adding it. So positive energy is energy, whoops, I hit the back of slide button. Okay, so energy going in, we're adding it. So that's positive energy. Energy going out, that's negative. So it's being released. So you can think of it like a bank account. If you are adding money to your bank account, you're going to be using the plus sign to add that value to your total. If you're withdrawing money from your bank account, you're going to be using the negative sign because you're taking it out. Okay? It's the same thing with energy and chemical substances and making and breaking bonds. If you're breaking the bond, you need the energy, you're adding it in, we have positive energy. If you are breaking the bond, if you're making the bond, you're going to be releasing the energy, and if you release the energy, it's exiting, so it's negative. And so we could graph that change in energy. And so Here we have this is called a reaction coordinate diagram. And so we have the energy on the y-axis here, and we have the reaction progress on the x-axis. You can kind of think of this as the time as well. That's another way of thinking about it. And so over the course of the reaction, the energy is going to change, and that's what this is showing. And so we have reactants going to products. And of course, that is what we'd expect for a chemical reaction, because all chemical reactions start with reactants and they react to yield products. And so going from left to right is our chemical reaction, just like in our reaction coordinate diagram, we're going from left to right. And so if we're starting with the energy of the reactants right here, and the products are going to be down here, that means overall going from, so if I were to trace this back down to the axis, if I were to start up here and I would end up going down here, well, the energy decreased. An energy decrease means the energy is leaving. So think about our system. If energy is leaving, then it's, in other words, it's exiting. So if it's exiting, it's negative energy. So that would be what we call an exergonic reaction. Exergonic means energy is leaving. And so the way you could remember this is, for exergonic reactions, we have the prefix X right here. And so you can kind of think of that as to exit. So exit is a good way to remember that. So this is an exergonic reaction. So when you're looking at these diagrams, you're just comparing the reactants to the products. If the product energy is lower than the reactant energy, then something happened to the energy. It left the system. It was released. It exited. You'll also notice that there is this kind of hump in the diagram. So we have to overcome a certain amount of energy to get the reaction to go. And that energy that we have to overcome is called the activation energy. So a good example for this is like striking a match. The match head has the chemicals. It has the phosphorus in a compound with a stabilizer attached to a wood stick. And then it's surrounded by the oxygen in the air. Okay, so we have all the reactants we need. We have the phosphorus, we have the oxygen, and those react to combust to form our flame, right? So that's the reaction for a match. However, if I hold a match there, it's not going to just randomly combust. I need to get it going. And what do I do to get it going? Well, I add in my activation energy. Well, what's the activation energy for lighting a match? Well, it's the friction on the side of the box. And so we have that roughness on the side of the box, and actually that's the phosphorus, but the side of the box, it's rough, and so when we strike the match, it provides that friction, and that friction creates the heat, and that heat is energy, and that energy is what activates our chemical reaction. And so by striking the match, we are increasing the energy of the reactants such that it's high enough to reach the activation energy. So you can kind of think of like a ball rolling up a hill, okay? So if I have, imagine, so just look at this diagram. If I have a ball and I want to roll it up this hill, it's going to require some energy, okay? It's the same thing with activation energy. I'm striking the match. I need to put an input of energy in there. Once I get the ball up here, though, it's just the reaction is gonna go, because that ball will very easily roll down the hill with no more extra effort. And so that's where the energy gets released. I did have to put in some energy to get that ball to the top of the hill, but once it's to the top of the hill, it's just gonna roll right down, okay? And so that's, overall, we put in some energy, but the energy that was released far surpasses the energy that was required to put in. So overall, this reaction releases energy. So that's where we get the negative for the reaction. So this is going to be an exergonic reaction because energy is leaving the system. And so we could also think about this in terms of the heat. So exergonic is a term that just talks about the energy in general. But if we're talking specifically about the heat energy, then we could use this term exothermic. Okay, so exergonic, exothermic, or exothermic, these are both terms that talk about energy leaving the system. Okay, and so when we're talking about exothermic, we're talking about the heat leaving the system. When we're talking about exergonic, we're just talking about the energy leaving the system. Okay, and so in terms of exergonic reactions, so if this represented all exergonic reactions, exothermic reactions would be part of that. Okay, so all exothermic reactions are exergonic, but not all exergonic reactions are exothermic. And so here are some examples where heat would be released. Wood burning, explosion of dynamite, rust, burning of fossil fuels. Those are all examples where heat is released. And so when that heat is released, the reason why is because we are normally forming new bonds. So while it's kind of hard to think about chemical reactions in terms of what's going on and whether it's going to be exothermic or endothermic, it's a lot better to think about the heat involved. And so for wood burning, for example, we know that we are breaking the bonds in cellulose. So if we're breaking the bonds in cellulose, then you'd think the energy would be going in. But don't forget the second half of the reaction. When we break those bonds in cellulose, we are making new bonds of carbon dioxide, so the carbon and the oxygen bonds, and then we're making new bonds in the water vapor that's produced between the hydrogen and the oxygen. And so you have to think about the entire reaction. Reactions are bond making and bond breaking processes. So overall, if there's more energy leaving the system, then it's going to be exergonic. If it's heat energy, exothermic. If there's more energy going into the system, then it's endergonic or endothermic. Okay, and so I implore you to always think about what you see. So don't think about this on the particulate level. It gets too confusing. Think about it just on the macroscopic level. Wood burning, does that create heat? Yes or no? Yeah, we know that burning wood creates heat, so therefore energy must be leaving overall. So that would be exothermic. Explosion of dynamite, does that create heat? Well, yeah, it does. So that's exothermic. Rust, that's a very slow process. You might not realize it, but that also creates heat. If you were to condense the process of rust into a very short time frame, you'd be able to measure that. But since it's a very slow process, we can't. Burning of fossil fuels, burning of anything, we know that the energy is leaving. So those are all exothermic reactions where the energy is leaving the system. So when energy is going in, it's a different story. So this is our reaction coordinate diagram. So here, look at the reactants. They're starting down here, and look at the products. They're ending up here. So overall, we are gaining energy. So if we're gaining energy, think about our box, energy is going into the system. So it's positive energy. So energy going into the system, we call it endergonic. And for this word, I know it's not quite the same, but ender/endo for endothermic, I always think of the word into. So exo is exit, endo is into. Okay, and so energy is going into the system. And so we still have that activation energy that we talked about, but this time, once we get the ball to the top of the hill, it doesn't roll down as far. So if it doesn't roll down as far, then we're not releasing as much energy. Okay, and so remember, we need energy to break bonds. So whenever we're breaking apart bonds, energy's got to be input. Okay, and so endergonic reactions, it's any type of energy. So this energy could be in the form of light, like UV radiation. For example, hydrogen peroxide, H2O2, breaks down in light. Okay, so the light is the energy of activation required to make that reaction go. That's why we ship it in these brown opaque bottles so light can't get in. It could also be heat. Heat can activate a chemical reaction. Okay, and so that's more times than not. Think about your match, or think about lighting a firework or anything like that. And then electricity could also be the energy required for activation. For example, electrolysis, the separation of water into hydrogen and oxygen, that requires electricity. And so energy can be in different forms other than heat. It just happens to be that most often it is heat. So that's why we deal with the concept of endothermic and exothermic. And so whenever we're talking about thermal energy, that's when we're using the suffix thermic, because therm means thermal. And so, again, endothermic is just a small portion of the endergonic reactions. So endothermic are just the smaller portion. So all endothermic reactions are endergonic, but not all endergonic reactions are endothermic. So always just think about your system. And so for endothermic, heat is going in. So this is endothermic, and if it's just energy in general, then it's endergonic. So just like we have the conservation of mass, remember we dealt with conservation of mass, it's also the conservation of energy. All the mass that goes into a reaction comes out. All the atoms that go in come out. They're conserved. They're just rearranged. They're broken apart. They're combined. It's the same thing for energy. If mass is conserved, energy is also conserved. So all the energy that comes into a reaction must also go back out. Okay, so the law of conservation of mass is the same deal as the conservation of energy. So the chemical energy of all the reactants is going to be equal to the chemical energy of all the products plus any energy that was released. And you could also put it this way: the input energy plus the chemical energy of the reactants is equal to the chemical energy of the products. Okay, so it just depends on the type of reaction that you're talking about as to what's going on with the energy. In other words, let me erase all this. In other words, if I have a general reaction, A plus B yields C plus D, one that is an exothermic reaction releasing energy, I could symbolize that by putting energy over here on the product side since it's being produced. So this would be an exothermic reaction. An endothermic reaction would be one where the energy is going in, like that. So endothermic, it's coming in. Exothermic, it's coming out. Okay. And you could also think about it in terms of just general energy. It doesn't have to be heat. General energy coming in, endergonic. Energy coming out, then that's going to be exergonic. So an example that's easy to think about is photosynthesis and cellular respiration. So for photosynthesis, we have sunlight, which is our energy coming in, plus our glucose. That's cellular respiration. So sunlight plus our carbon dioxide plus our water yields our glucose, C6H12O6, plus our oxygen. Balance it, we have 6, 6, and 6. So that is our photosynthesis reaction. We could see our energy input is right there. We have an energy input, so therefore that is going to be an endergonic or endothermic reaction. Whereas cellular respiration, it's exactly the opposite. We're starting with our glucose, C6H12O6. We need our oxygen, 6 of them, and we're producing 6 CO2 plus 6 water. and this time we're releasing energy in the form of ATP, chemical energy. And so energy is leaving. So it's entering a photosynthesis, so this is an endo reaction, and then it's leaving in cellular respiration, so therefore it is an exo reaction. Okay, and that's it. And so were you able to answer the following questions? Can you identify the source of the energy changes in chemical reactions? How do exergonic and endergonic reactions compare? How do exothermic and endothermic reactions compare? Another one we could say is, what's the difference between exergonic, endergonic compared to exothermic, endothermic? And then how can we describe the conservation of energy in the reaction? Okay, so that is the lesson for 19.3.